Hello. So we will now consider another example with real data. The example is to estimate the returns to education, returns to schooling. And in this example, Y is wage, your wage, especially hourly wage, and X is the years of education. So if you graduated high school, then that's 12 years, and if you graduate 4-year college, then that will be 16 years, and like that, right? And so as you increase, as you get more education, then your hourly wage may be increasing, right? Will increase, I guess. So we would like to study their specific relationship, like especially beta 1. When x increases by 1 year, for example, if you get a master degree, how much the hourly wage will increase? It will increase by beta 1. And by the way, beta 0 in this case is the expected hourly wage when your education is 0. But is there any observation whose education is 0? No. These days, x equals to 0 maybe does not exist. So in practice, beta 0 has no real meaning. I'll explain that later. So because x equals to 0 is unrealistic, so the value of beta 0 will be estimated very inaccurately because there is no observation there, right? Maybe I'll come back to this point later. And our data is from National Longitudinal Survey in 1997. We used this data, no, we have not used it before. So let's go to Excel. Here, simply I took education and wage, two variables, and look at this. The first guy graduated high school, 12 years, 17 years. Maybe this person has a master degree, 1-year master program, and 18 years, maybe 2-year master program, and 14 years, 2-year college, or drop out of college. So like that, there are people, there are 2,244 observations, 2,244 individuals in our data, and of course we observe their hourly wage. So it's 1997, so it's a little bit outdated, but a good data set for educational purpose. So you can just check what's going on. By the way, there is a guy who has 0 education. Oh, it does not show you correctly. So I used a filter, and there are some guys who have very low education. I don't know how it's possible. Could be error, like 10 was mistyped as 0. Well, I don't know, but I have to take it as given, right? 0. And wage ranges from about $1 down to $40. Someone is making $40 an hour, while another person makes only $1 an hour. And then the idea is the same. We are doing the same regression data analysis. Choose Y. Here Y is wage because we are explaining wage using education. So Y is wage, hourly wage, and X is education, right? And the first line is label. Here I will show you a few options, like you may change the confidence level to say 99%. Then in the results you are going to get 99%. And if you check this box, then the results will come with a plot, scatter plot. Let's see, let's try. The problem is you have to specify the area better. I just choose column B, but it did not work. You have to choose up to this point, and from there to goes forever. Yep. Without dragging, you can just click Control Shift and arrow, but I just did it by mouse. Okay, I choose it, and first this is the plot I ordered. I checked the option, so it shows distribution. Education ranges usually between 4 to 18, but I don't know what they are, but there are outliers at 0. There are outliers at 0, 2 observations at 0, but most of the people should be on 12 high school graduation or 16 college graduation. There may be some people who drop out of school before graduation, but it's hard to see from here. And then the red line is the predicted trend line. So linear regression can automatically calculate this. So the red line shows a trend which is clearly increasing, right? And another thing you can find here is it goes below 0. That is very weird. Wage cannot be negative. Hourly wage cannot be negative at all, and there is no negative observations at all, but it is estimated to be negative. It's because this is outliers. They are outliers. So estimator in this area is very inaccurate. The most of the data here, so estimator estimation on this area should be much more important and accurate. So ignore, it's not a big problem, and it's not easy to interpret. And, let's close that. This is an option. And residual output, like we are going to learn residual in the next time, so ignore that. Excuse me. And here, because we chose 99% confidence interval, it calculates 99% confidence interval along with 95%. So if you are interested in a specific confidence level, you can choose the option in regression setup. Okay, now let's see what happened. First, education. The coefficient of education is estimated to be 0.73172864, whatever. So let's say 0.7 simply. This is the education. That means if you attend school for another year, your hourly wage is expected to increase by $0.7 per hour, right? And its accuracy, how accurate that estimator, that's like measured by this standard error. By the way, let's reduce the decimal places, right? So standard error of that estimator is 0.046. So this coefficient has, this estimator has this much potential standard error. And the t-statistic is 16, which is huge, and p-value is 0, and confidence interval at 95%, 95%, and confidence interval for 99% are given. So this is the same thing, and again here also look at here, number of observations is 2244, and standard error. Standard error is 5 point something. Standard error is quite huge, which you could see from the plot. The deviation was huge. There are huge deviation, like huge variability, huge inequality in wage, as you know. So the standard error of the regression model is larger than the simple example. Okay, then using the data, basically this is the results. This is what you need. Or you may open your own Excel and try that. Then can you calculate the 95% confidence interval? Try it yourself. When you have the results with you, it will be simple. Or you may calculate the confidence interval using these results. So it doesn't matter which way you do, but I want you to do it somehow using Excel or using algebra. Well, like you have to do either one of them. The answer is, let's look at the results. 0.654.833. That is 95%. 654,833. C. I don't know why there is a rounding error. But maybe if you use these numbers, then you may have a rounding error. That is given, right? There may be rounding error somewhere, especially in here. This number, 1.96 is already rounded number, so this should be more accurate, right? Okay, confidence interval can be calculated this way. And now I will ask you this. Can you carry out this hypothesis testing? Again, you may use your own algebra, or you may look at the results. Do it by yourself and find the number from Excel. Calculate the t-statistic and make the decision. If you have done, otherwise pause the video. The answer can be found here. T-statistic is 16 point something. So 16 point something. So C or D. Again, I calculated this number based on these guys, these rounded approximate numbers. So there may be rounding errors. So like these numbers and these numbers. Anyhow, 16 point something is the t-statistic. And then t-statistic is very large. So you have to reject the null hypothesis. So large t-statistic means the difference between the data and the hypothesis is too large. So reject the null hypothesis. The answer is C. Okay? And as a result, you can say the coefficient is statistically significant, right? By the way, p-value can be found here. So you don't need to worry about the decision because p-value is here. So you can simply compare the p-value with 5%. Anyhow, it is rejected. Anyhow, because the null hypothesis is rejected, your model is now statistically significant. Your coefficient, so education explains something about the hourly wage. So statistically, it's meaningful, right? It means something. So which is good for you, right? And then, yeah, I explained. By the way, there is another thing I have to mention here. Another difference is that I taught everything based on the sampling distribution of and the central limit theorem, the normal distribution approximation, but Excel uses t-distribution approach, which I briefly introduced at the end of the sampling distribution chapter. But in the end, as you can see, the difference is just like kind of rounding error, right? Because already the sample size is more than 2000, so the approximation error should be ignorable. I believe there is little difference. Even larger error may arise from this approximation and this approximation, right? When we drop some decimal places, they cause some errors. So maybe like that, errors may happen here and there, but this is not a big deal, right? I don't worry too much about the difference. And finally, I will ask you another thing. We may do one-tailed test in this case. right? Because we have everything. Now it is not in Excel. You have to do it by yourself. So our estimation results are here. Use these numbers. And we are considering upper tail test. You believe that the effect of education is no greater than $0.7 per hour. But someone else is insisting that the effect of returns to education is greater than, strictly greater than $0.7 per hour. So lower than 0.7 is not a problem. You are arguing whether it is greater or not. So in this case, so it's an upper tail test. Remember, in this case, you reject the null hypothesis only when your observation, your data is larger than a certain level. So try to calculate the p-value in this one-tail test. Pause the video. I will show you the answer. The answer can go like this. So t statistic goes like this. Beta 1 hat estimator minus your hypothesis, right? So estimator minus hypothesis is standardized by its standard error, which is also given. So estimator, standard error, and your hypothesis. Consider these three numbers, and then the t-statistic is 0.93. Given the t-statistic, because we are considering an upper tail test, the p-value only includes probability above that t-statistic. So probability greater than 0.93, which is about 17%. And 17% is greater than like 10% usual significance levels. So in this case, this hypothesis is not rejected. So if you believe that the returns to education is $0.7, then that's not wrong, right? That's what you can tell from here. And as you just saw, we may apply all the same framework we learned earlier into the regression model. So this is the statistical properties of a regression model. And I'm going to call it a lecture, and in the next lecture we will consider prediction, which is the main purpose of the regression model. Okay, see you in the next one.